Continuing with the graph neural network series, and in this video I'm covering graph convolutional neural networks for web scale recommender systems, or PinSage for short. And as you can tell by the title of the video, it's going to be more about like this huge engineering system that's deployed at Pinterest than about novel algorithms like propagation rules or something like that. So anyways, one thing worth mentioning is that this is a direct continuation of the GraphSage paper, which I've covered in my previous video. So if you don't know anything about GraphSage, it's probably a good idea to just go and check out that video. I'll link it somewhere somewhere here. So basically, the authors are basically the same. Rex, Ying, Hamilton, and Leskowitz were the authors on GraphSage paper, and we have some additional authors for PinSage here. So let me start. We describe a large-scale deep recommendation engine that we developed and deployed at Pinterest. And I so happen to have opened a new account today, so let me just show you how it all functions. So basically, and why I'm showing you this is because they're training PinSage for two specific recommendation tasks. The first one is this home feed recommendation, where basically the goal is to give you most relevant pins on your home feed. And the reason I'm mostly having like motor cars here and motorbikes is because the only pin I have is of a muscle car. So initially I just picked some categories, and what Pinterest did was it gave me pretty much uniformly from all of those categories a couple of pins. And what I did, I went and pinned a certain pin, and now I'm pretty much getting related pins to the last pin I've made. And we'll see that in the paper they actually explicitly mentioned that that's how this home feed recommendation works, and it seems they haven't changed that thing. So another task they are doing is if I open a specific pin, and what they do here is they offer you this list of similar pins, so more like this. So these are the related pins to the pin you're just chosen. And there is also, aside from the concept of a pin, they have something called boards. And so this user, Harry, saved this particular pin to this board VROAD. And basically boards just basically accumulate similar pins in a logical unit. And that's everything I wanted to cover. Let me get back to the paper. So they say here, we deploy PinSage at Pinterest and train it on 7.5 billion examples on a graph with 3 billion nodes representing pins and boards and 18 billion edges. So hopefully, because I went through the platform, if you're not familiar with Pinterest, this will kind of contextualize both the problem and how everything fits together. So let me start and show you some engineering innovations they introduced, as well as some algorithmic innovations. So first off, they say here, traditional GCN algorithms perform graph convolutions by multiplying feature matrices by powers of the full graph Laplacian. And what that basically means, if you're familiar with GCN, and here I'll open this paper which I've covered in one of my previous videos, and you can see the update rule for GCN, and basically this part, the A tilde part, is in a structure similar to Laplacian, even though it's not Laplacian, and that's what they're basically saying. They're saying that you need to store this whole huge adjacency or Laplacian matrix, which is m by n, where n is the number of nodes, and in the case of Pinterest, we have like 3 billion nodes at the time that the paper was written, and so basically that's not an option at all. So let me get back here. So what they did is the same as in GraphSage. They are just subsampling the neighborhoods, although they are not doing uniform sampling. They are doing something more clever, and I'll get to that in a bit. The second thing worth mentioning is that they have, so on the engineering side, is that they have this producer-consumer pipeline. And basically what it means is that we have, in parallel, the CPU is preparing mini batches while the GPU is doing propagations, and then you can just optimize and sync them so that GPU is never starving. And they say it here, CPU-bound producer efficiently samples node network neighborhoods. A GPU-bound TensorFlow model consumes those. And thirdly, they have this efficient MapReduce inference. And why do they have this? Well, basically, and we'll see that in a bit more detail. But the Pinterest graph is huge, and what they do is they train the PinSage model only on a subset of that huge graph. And once they have the model trained, they just use this MapReduce pipeline to basically compute the embeddings for every single other node in the graph. That's pretty much it. So they say here so MapReduce pipeline can distribute the trained model to generate embeddings for billions of nodes while minimizing repeated computations. So this is the important part. And just on a small tangent, let me quickly explain the MapReduce pipeline, and it's really simple. So I thought it's worth mentioning it. Basically, here on an example, this is a canonical example of doing finding word frequencies in a document in documents. And here is just a toy example with 3 sentences. You can imagine a huge corpora here, like imagine transformers which have multiple terabytes of textual data, which needs to get somehow maybe like the word frequency needs to get calculated. And here on this example, what happens is we basically have 2 modules. We have this mapping part and we have the reduce part, and hence the name MapReduce. And basically inside the mapping module, we first just split the data. So here every single sentence will go there in a separate module. And what then happens is we just map those parts, those samples of data into key value pairs. And in this example of figuring out the frequencies of the words, we basically end up with like deer having 1, bear 1, etc. And then what we do is we shuffle, which is basically clustering these key value pairs by the key, and we end up with these. And finally, the reduce stage sums these values up. And it depends on how you define those reduce and map scripts. And finally, you just aggregate those and you get the final result. Every single word has its frequency associated with it. And this is a simplified example. Obviously, you'll have multiple shuffling and reducing stages in a real production system. So again, it's supposed to minimize repeated computations. And if you're familiar with GraphSage, this will be really this image will make sense. If not, I'll briefly do an overview as well here. But like the repeated computations are these here. So basically, the node A, this computation here is the same as this one here and the same as this one here. So what MapReduce does is it does this projection only once for every single node in the graph, and thus saves us a lot of computation, unnecessary computation. So that's the role of MapReduce. And on a short note, how this works is the following. So let me take, I'll just ignore, because these are 2 layers of the PinSage algorithm. I'll just ignore one layer and I'll focus on a single layer. And basically, to calculate for a specific node, and we can see a toy graph here, and we are interested in this target node. So to calculate the representation of this node A, what we do is the following. So we basically concatenate its last layer representation with the aggregated neighborhood representation, which we again get by doing some aggregation. And in PinSage, they introduced this thing called importance sampling, importance pooling, and I'll explain that in a lot more detail a bit later. But for now, just this is some aggregation function. Like in GraphSage, you had max pooling, you had LSTMs, means. So this is something similar. And so what we do is we take the neighbors, and you can see B, C, and D are the neighbors of A here. So we take those neighbors, we just project their representations here, and we aggregate them. And that's how we get the aggregated portion. So that's how the algorithm works in a nutshell. There are a couple of innovations which I'll now briefly do a high level of. And so these are the innovations in algorithmic sense. Basically, they show that the random sampling, uniform random sampling they used in GraphSage is suboptimal. So they do this thing called importance pooling, where they are basically picking those neighbors which have the most influence on the target node, and that will get clear in a couple of minutes. So they say here an additional benefit is that each node now has an importance score, and those scores will be used in this importance pooling. I'll explain that a bit later. One more algorithmic innovation is this curriculum training, where basically the algorithm is fed harder and harder negative examples, and we'll see what those exactly are in a couple of minutes. So that's a high-level overview of what the both the engineering as well as the algorithmic innovations are. And now I'm going to slowly dig into details of this paper. So first things first, the tasks, as I mentioned, are related pin recommendation and home feed recommendation tasks. And we saw that on the platform itself. So just keep that in mind. So in terms of the algorithmic design, they are basically, as I said, continuing the GraphSage paper, so the work on that paper, and they took a couple of ideas from FastGCN by Chen and his collaborators. Basically, the importance pooling part, those ideas were borrowed from this paper. And again, engineering details, and I'll have a lot of these throughout the video, because this paper is there is a lot of engineering that went into this work. So I think it's just worth mentioning some of them, and I'll omit like most of them, but I still want to mention a couple of them. So we fundamentally improve upon GraphSage by removing the limitation that the whole graph be stored in a GPU memory. So basically, they are using that producer consumer pipeline, so we don't have to hold the whole graph in GPU, you hold it in CPU, and that's where the producer is, and then the GPU, the consumer, just takes mini batches, and basically that's how it trains. Okay. One more thing to note, they mentioned here why we can't use those shallow graph embedding methods, so like deepwalk and node2vec. The reason is they basically have for every single embedding is stored in a table, in a lookup table. So this table would be huge, like because this is n, and that's the number of nodes, and because Pinterest has like multiple, like billions of nodes, this is like pretty much intractable. And not only that, but it's also inherently transacting method, which means it will have to get re-optimized to get when new pins are introduced into the system, which is also not desirable. And lastly, these methods only use the co-occurrence statistics of the graph, and they can use the features. And as you probably can assume, pins in this graph have rich features associated with them, because they have like imagery, and they have like maybe some, let me draw something here, okay, and they also have textual information associated with them, so these methods can even make use of these. So yeah, those are multiple reasons why you just can't use those graph embedding methods for this task. Okay, let's continue and see how they structure, how they model the problem. So basically, they model the graph the following. So you have on one side you have pins, or more generally items, and on one side you have boards, or more generally collections. And what they do is they just create a bipartite graph, where basically, as we saw, one board has multiple related pins associated with it. So this is how the graph will look like. Something like this. And they mentioned they have around 2 billion pins and about 1 billion boards. So this is how the graph looks like. And yeah, I mentioned this, pins are associated with both rich text and image features, and the goal is to leverage both the features and the graph structure to find those embeddings, which can later be used to recommend related pins, etc. Okay, so now that we know how the problem is structured and what the tasks are, and let's dig into some details. Yeah, by the way, they treat both the pins and the boards as the same nodes, even though only the pins basically have features. So they say here, for notational convenience and generality, when we describe the PinSage algorithm, we simply refer to the node set of the full graph with V. So it's a union between items and collections, and they do not explicitly distinguish between pin and board nodes. Okay, this is the algorithm. Basically, if you're familiar with GraphSage, it has the same structure, same old structure. So here, this one line corresponds to this line. concatenation corresponds to this line, and normalization corresponds to this line. There are a couple of innovations though. The first one is how they sampled the neighborhood. That's the first innovation. The second one, importance pooling. And that's pretty much it. There is not a lot of new things that happen here. Everything else pretty much remained the same. So a couple more notes before I explain the importance pooling and before I explain the neighborhood. So they say here, empirically we observe significant performance gains when using concatenation operation instead of the average operation as in 21, which is GCM paper. So basically this here, they showed empirically that it's better to use concatenation than just the thing that GCM did, and that's just pretty much scaled, weighted mean of these features. And secondly, the normalization part, so this part here, in line 3 makes training more stable, and it's more efficient to perform approximate nearest neighbor search for normalized embeddings. And I'll explain what that is in a sec. So first, normalization, what it does, it basically makes sure that all of our embeddings lie on a hypersphere. And that's just a fancy name of saying a sphere in higher dimensions. If that sphere was in 3 dimensions, basically we'd have that sphere lying around the coordinate beginning, and all of the embeddings would lie on the edge of that sphere. Hopefully you can see that. So again, maybe here we have a huge sphere, and all of the embeddings lie somewhere on this sphere. All of our pins, all of our boards lie somewhere on this sphere. So they say here, it's more efficient to perform approximate nearest neighbor search. So why do we care about approximate nearest neighbor search in this context? So the reason is pretty simple. So you basically have the embedding space, and you embed your pins, like maybe you'll maybe take this motorcycle and you'll embed it here, and that's pin 1. And then you'll have all of the pins embedded. And basically, if you want to do related pin recommendation, what you pretty much do is you find the k nearest neighbors to this target node P1. So if I'm interested what the related pins to the motorcycle are, I just find the closest ones. And now because there are so many embeddings in this space, so there are billions of embeddings, we can't do exact nearest neighbor. So they just use methods such as locality sensitive hashing, which are really good approximative methods to do k nearest neighbors. So that's why they mention nearest neighbors here, and so normalization helps calculate those nearest neighbors. Okay, with those details out of the way, let me explain the 2 most important parts, and that's neighborhood and importance sampling. So basically, this is how it looks like. We have a target node, and we have its neighborhood. So this is the 1-hop neighborhood, this is the 2-hop neighborhood, 3-hop, etc. So what we do basically is the following. We take a bunch of random walks which are decently short, and we run them in parallel. And what we do is we just count up the number of visits that every single node had. So this one maybe had 2 visits, this one had only 1 visit, maybe some of them had 3 visits, like this one maybe had 3, this one maybe had 3. And we basically take the T nodes that had the highest visit count, and that's it. So T was 15 in their scenario. So one thing worth mentioning is that these random walks are not biased. And what that means is basically if you're at this node, you'll go to your next node will be one of the neighboring nodes with equal probability. Contrast that to biased nodes, such as node to vec, for example, method used biased random walks, where if you have some parameters there like P and Q, and depending how you set them up, you'll either prefer going in a BFS manner, so breadth first search, or you'll be preferring depth first search, traversals of the graph. So here we just have pure unbiased random walks. We figure out, we run multiple of them and in parallel, and we just find the counts, and that's our neighborhood. So for example, if T was maybe 3, we only take this neighbor, we take this neighbor, and we take this one. And so how does that fit into importance sampling? Well, it's pretty easy once you think of it. So basically, what we do is we take their visit counts and we just normalize them by the sum. So this will be 3, 3, and 2, that's 8. So we'll have the final weights will be this. And then the importance pooling part just works. You just take these weights, you sum up their projected representations, and so you multiply the representations, the projected representations by these weights. So this one, so this representation, this feature vector will get multiplied by this one, and this feature vector will get multiplied with this weight, and you just sum them up, and that's the gamma part. That's the importance pooling part. So contrast that to GraphSage, which just had max pooling, and there we didn't have these weights. We just find the like element-wise max, and that's the difference. Okay. So they mentioned here the neighborhood of a node U is defined as the t nodes, and I mentioned that's 50 that exert the most influence on node U, and it's pretty much intuitive that all of those nodes which had the highest visit counts are in a sense the most influential ones, because we have the highest probability of visiting them. They are the most connected in a way to our target node U. And again, about the importance pooling, we implemented gamma as a weighted mean with weights defined according to the L1 normalized visit counts, which is the thing I just explained. And they refer to this as importance pooling. So those are the main innovations they had. But there are some more things that I want to cover. So let's just continue with model training. So if you remember GraphSage, how GraphSage was trained, it was basically trained either in an unsupervised manner using negative sampling, or we had task-specific supervised loss, like cross entropy in the case of classification. So here, PinSage uses this thing called max margin ranking loss, and we'll see what that is in a sec. But before that, what's the data? So the goal of the training phase is to optimize the PinSage parameters so that the output embeddings of pairs query and I from this set L in the labeled set are close together. So what's this set L? So basically what it is the following. They just track the engagement on Pinterest. So if you, for example, if you were playing with pin Q, and the first next pin that you opened or interacted with, had an engagement with, was pin I, then they just put this pair in this set L. They just add this pair to this set L, and that's how they collect basically the supervised data set. Just through natural engagement of users on Pinterest, they through time get a huge training set L. Okay, now let's jump and understand how the loss works. And I'll skip through this mini batch version of the algorithm I just showed you, because it's equivalent to the GraphSage algorithm. They just, instead of working on the whole Pinterest graph, they just take a subset and they just work on that subgraph instead of using the whole graph. So I'll just skip it for now. And let's focus on the loss function. And this is the interesting part. So basically, the following happens. So ZQ, ZNQ, all of these are the final representations that you end up having after you run the PinSage algorithm. So you end up with these Z vectors. And once you have them, what you do is the following. So you have Q, which is the query embedding, and you have positive samples, which is Zi, and you have negative samples, which is Nk. And the goal here is the following. You basically want to make sure that the similarity between Q and I, which is by definition a related pin, this thing should be bigger than the similarity between Q and this negative sample by at least a margin. So for example, if this similarity was 3 and the margin was, which is a hyperparameter itself, so if the margin was 2, that means we need to make sure that this part is at least 5 or bigger, 5 plus. And why is that? Because we have a max between 0 and this term here, which means the loss goes to 0 once this becomes negative, and this becomes negative once this part becomes bigger than the similarity between the query and negative sample plus the margin. So that's this portion of the loss. Now, if you're like me, you're probably confused, or you were confused at one point of your life with this part, the expected value. And what this basically says is the following. So the higher the probability of a certain negative sample, the more important it is to minimize its associated term here. So let me try and visualize that here. So basically, first maybe a mathematical definition of what the expected value is. Maybe it will be, for some of you, will make sense. So expected value of a random variable x and some function g of x, where this small x is just one of the possible outcomes of this random variable big X, is the following. It's just a plain sum of the probability of those outcomes times the value of the function g at that particular outcome x. And let me now contextualize and associate these two. So g of x is basically this part, this max part, and let's see where the p part comes from. So if we have a graph like this, if we have a graph and we have a couple of nodes, and maybe this is the query node and this is the related node, that's ground truth because of the engagement and the way how Pinterest collects these. So we know this is the related one, and we know this is the query pin. So now let's say there are a couple there. So every other pin, every other node in the graph is a potential negative sample, assuming that this is the only related pin to query pin. So what we do is the following. So let's say that during the training we maybe take 7 times we take this node as a negative sample, as the nk. So remember the notation, we had znk. So 7 times. Maybe we take this one 1 time, maybe we take this one 0 times, and this one 2 times. So basically what happens is, because this one was sampled most oftenly 7 times compared to 2 and 1, it's really important to minimize its associated value, so g of x, to be as close to 0 as possible, right? Because we'll have 1 time something, so the loss will be 1 times x plus 2 times, so this is 2 times its loss, that's y, plus 7 times z, where z is the loss value associated with this negative sample. So that means it's the most important. So the most important thing we can do is minimize this part. So because this is the highest, the highest number, and if we translate these into probabilities, into empirical probabilities, because we had 10 times, we draw negative samples 10 times, this would be 7 over 10, this would be 2 over 10, and this would be 1 over 10. And that's where the p of x comes from. So basically we have 0.7 times this max, and that's the reason we want to make sure that the higher the probability, we want to make sure that that term is the lowest. Okay, hopefully this wasn't too much confusing. Okay, let me continue. What else? Again, some engineering details. We design a producer-consumer pattern to run GPU computation at the current iteration and CPU computation at the next iteration in parallel. So that's what I mentioned already. And this further reduces the training time by almost a half. So even though conceptually this is a small thing, like it's A, really hard engineering problem, and B, it led to like a huge improvement in efficiency of the algorithm and training time. Okay, and one more engineering detail is that they are to improve efficiency when training with large batch sizes. We sample a set of 500 negative items to be shared by all training examples in each mini batch. So they won't be finding for every single node, they won't be figuring out the negative examples. They'll just pre-compute 500 negative items, and they'll be sharing those for different query and related pins. Enough about engineering details. Let's see one more important part. Algorithmically. So, however, ensuring that the inner product of the positive example, so pair of items Q and I, is larger than that of the Q and each of the 500 negative items is too easy. And why is it too easy? Because if you take a random negative example from the huge data set they have, like multiple billions of pins, there is a huge probability that it will be totally different from the related pins, and that means it's really too easy to optimize this problem. And here they show they show an example of what they mean, and they mention here, so to solve the above problem for each positive training example, so the item pair Q and I, we add hard negative examples. So we make a distinction between hard negative examples and like maybe easy negative examples. And you can see it here visually. Basically, this is a query. So we have some flower on an embroidery, and then we have a positive example. So that's the I pin had this image, and you can see it's also an embroidery and it's also a flower. So a random negative example, so the easy negative sample would be this. So this is neither embroidery and it's neither a flower, so just some random hat. And this is the hard example because it is embroidery. So it's a similar, in a way similar to these two, but the content is a bird instead of a flower. So that's what makes it hard. Okay, so now that we know that, let me see what they do and how they calculate. How did they figure out these hard examples? So they are generated by ranking items in a graph according to their personalized page rank scores with respect to the query item Q. Items ranked at 2,000 to 5,000 are randomly sampled as hard negative items. So page rank is, you probably heard of it. Page rank is Google the initial algorithm that Google used for its search, and intuitively it just looks at the edges and using that finds how important a certain web page or element in general is important, depending on how many links point to that particular node. So what they do is they take the query pin and they just calculate these personalized page rank scores. They just sort them by the score, and they just take, for example, from 2K to 5K. They consider, so there's just some heuristic they figure out makes sense, and they just randomly sample elements from this subset, and those are the hard examples in the training. And for the part, so this part tells us about the curriculum learning. So in the first epoch of the training, no hard negative items are used, so that the algorithm quickly finds an area in the parameter space where the loss is relatively small. At each epoch n of the training, we add n-1 hard negative items to the set of negative items for each item. So that means in epoch 2, they'll be adding 1. So that's n-1. So they'll be adding only one hard example. As the epochs progress, at epoch 10, they'll be adding 9 negative items to the set of negative items for each item, and that's how they progressively stimulate and make it harder to optimize that loss. Okay, that was all I had to say about the some things were about engineering, some things were about algorithmic innovation, and now let's switch topic a little bit and see how they tested this thing and what they did. So again, just a fun fact. So for the home feed recommendation task, we select the pins that are closest in the embedding space to one of the most recently pinned items by the user. And if you remember, I initially showed you that I have a bunch of cars here, and the reason, and motorcycles now, because I was interacting with a motorcycle, but like basically the last pin you made is heavily influences this home feed recommendations, and I can just empirically see that and verify it. Although it's not as simple as we saw, like this motorcycle, me engaging with this pin change my home feed here. Okay. So again, I mentioned this. They define the set L by using the historical user engagement data. Okay. Before we see some results, let me just detail a little bit how the features for every single pin are constructed. So basically, every single pin has some image associated with it. So that's some image. And then we also have some annotations, so textual information, and this node also has some connections with some other nodes. So how they construct the final feature vector is the following. So they pass the image through a VGG network. So there's just a convolutional neural net, and they take one of the feed-forward activations, and they use that as one part of the feature vector. Then they do a word-to-vec. They train a word-to-vec model on the annotations, and they embed the annotations also in a, I think it was 256 dimensional vector, and they concatenate these two. And finally, they add the log of the degree of this node, of this particular pin. So this is the degree. So maybe this node has, just ignore these. So we have four nodes connecting to this one. So we'll just add log 4 as a feature. So in a general case, log di, where this is node I, and this is the degree of the node. And now that we know how the feature vectors are constructed for the pins, for pins in PinSage, let's see how the baselines are constructed. We have this visual baseline, which basically does the following. So for every single pin, it just takes the image that's associated with that pin and does the same thing as PinSage. So it just passes it through a VGG network, takes out those features from certain fully connected layer, and embeds that directly, uses that as the final embedding. And so once you embed this thing into embedding space, how you recommend, how this simple baseline recommends is just using k nearest neighbors. So the same as PinSage, it just has a much less delicate method. It doesn't use the graph information, the graph structure. It's a content recommender system. Okay, second baseline is super similar, just uses only annotations instead of the image, so it uses textual information. Third one combines both of those and trains MLP on top of them. And finally, the fourth one is Pixie, which uses random walks to find the recommendations, and basically doesn't use those features, just uses the random walks. So that's the method that was previously used in production at Pinterest. Okay, and they don't compare with other methods because basically the scale is so huge that none of the previous methods could be simply used in this setting. Finally, they just modify PinSage in a couple of ways and use those as baselines as well. So here, this max pooling one uses, instead of using importance pooling, it uses max pooling, and it just doesn't use those hard negative samples which I showed you previously. So yeah, those are the baselines, and now we'll see the results. Again, some engineering details, huge pages, Hadoop, which is an open source implementation of the MapReduce framework, which I previously showed you and explained you. So, yep, let's see the results. Unfortunately, these are not metrics you're probably familiar with, so let me just briefly explain what these are. So we have something called hit rate. hit rate, and we have something called mean reciprocal rank. And what hit rate is the following. So basically you have the query pin and you have the related pin I, which we got by collecting like through engagement data, right? And so now our recommender system basically gives out a list of related pins to this query pin, and the length of this list is k, which is a hyperparameter, and they used 500 in this paper. So now what the hit rate is the following. So we are interested whether this ground truth pin is somewhere inside the recommended pins. If it is, we that's a good thing. If it's not, that's a bad thing. And basically hit rate just tells you going through the test set, so going through various queues, these queues and various eyes, you basically see the percentage of time that the ground truth pin appeared in your recommendations. And okay, looking at that, you can see that PinSage has 67% hit rate compared to these simple baselines like visual annotation and the combined. So the combined one is better as expected than purely using text or images, and PinSage is also better than all of these maybe simpler baselines of PinSage. So the second metric is this mean reciprocal rank, and you can see the formula here, and let me just make some sense out of it. So basically it's super similar to hit rate, except that we are interested into where exactly this ground truth pin I appeared. So let's assume that among the recommended pins, we did have this pin I, and it was a location maybe 256. Then that's much worse than having it at location 1, right? So if we'd ideally want to recommend this ground truth pin somewhere closer to position 1, and that's this R term here, and they just sum up those values and they just divide it by the number of nodes in the test, and that's it. And if you take a look, and 100 is just hard-coded, so it's just an empirically chosen value, so that once we have, so that we can distinguish when this is on a position to 1000 versus 2000, and that should still make difference. Otherwise, if this wasn't here, the difference between 1 over 1000 and 1 over 2000 is super small, and this makes it bigger. So that's the reason they put 100 here. And again, looking at the mixed reciprocal rank, we can see it greatly improves with PinSage. So those were the offline evaluations. They also did A/B testings and user studies, and I'll get into those in a minute. But first, one more important analysis they did is the exploration of the embedding space that the PinSage method created against these baselines, so the annotation and visual baselines. So basically what they did, so they took the embeddings, so you have a bunch of pins, and they are embedded. And you just take two random pins and their embeddings, and you do the cosine similarity. So basically you're interested in so if these are embedding vectors, so you're interested in cosine of the angle between them, cosine theta, and you just plot that, and you'd ideally want that to be distributed as much as possible, because that means they are not all of the embeddings are similar and similarly oriented. You want to have them, or if you pick the random pins, you want to have them randomly distributed in space, oriented in space. So looking at the graph here, you can see that the PinSage has the most distributed curve here, and the worst one is this one, because it's really close to 1. So you get 1 once you have, because all of the embeddings, remember, they are normalized to unit length, unit norm. So that means this one, you get 1 only when the vectors of the both embeddings totally coincide. And if you take a look at the annotation baseline, you can see it has the worst results. So it's 14% hit rate against 17 and 0.9. So it's the worst method. And these curves here tell the same thing pretty much. And if you can introduce some fancy mathematics into this, statistics. So basically the kurtosis statistical measure of the cosine similarities of PinSage embedding is 0.43 compared to 2.49 for annotation embeddings and 1.20 for visual embeddings. So you want to have this as small as possible. This pretty much measures how heavy the tails of the distribution are. So that's this statistical measure, the kurtosis. Okay. So those were the offline metrics and this analysis of the embedding space. Now, for the user studies, so they basically formed a group of people and they gave them a side-by-side different baselines. So PinSage and visual baseline, PinSage and annotation baseline, PinSage and Pixie, and they asked them which one is more relevant to the query pin. So this is the query pin, and then they give them some results from different baselines, and they ask them what's better. And you can see, so first the table, again, PinSage has the highest fraction of wins, so that's not much information there. So let's see some visual results. So given this query pin, where you can see some like young plants here, the visual baseline makes some semantical errors. So it returns the imagery of food, which is visually related, but it's not what we are interested in. It's not as related conceptually. On the other hand, annotations are returning some plants, Pixie also, but like none of these are as relevant as PinSage, which basically also gave both visually similar things, but conceptually the topic that's the same. Those are also some like young plants here and here and here. So you can see visually that PinSage gives the best recommendations. Finally, one more example. Here we see some logs in the query pin. So the visual one again made mistake, giving some war photos, which are like grayscale, and confused them thus with the topic that's similar to this one, and that's just logging. And you can see that PinSage gave both the visually similar pics and, most importantly, the most relevant pictures, pins in general. Okay. I mentioned they did A/B testing. So what they were testing in production is they were testing home feed, and they were testing this re-pin rate. So a user saving a pin to a board is a high value action that signifies deep engagement of the user. So once you recommend something to the user on the home feed and the user engages with some of the pins and saves them into some of his or her boards, that's a really good signal, and that's what they were testing like in A/B tests at Pinterest. So I assume they took some geographic location, they used some baseline there, and then took some other location, they took PinSage, and they compared how much the engagement varies between the different production systems. And they figure out that PinSage is again performing better. So all of the three metrics, both the offline metrics, both the user studies, both the A/B tests, show that PinSage improved the results. So let me wrap up the paper. Basically, a couple more details. This one is interesting. So after training completes, due to the highly efficient MapReduce inference pipeline, the whole inference procedure to generate embeddings for 3 billion items can finish in less than 24 hours. So this is impressive. And you can see how much engineering went into this system. And yeah, it's just, there's a lot of innovation happening in engineering also. It's not only about research. A couple more interesting charts here. So what they did is they took the embeddings of PinSage, and they just did some t-SNE reduction to 2D chart, and you can see that if I zoom in, embeddings that are really close in 2D space are topically similar. So you can see some fashion images here, you can see some covers here. So yeah, all in all, semantically, it makes sense. Finally, they were exploring the number of neighbors. So if you remember how the neighborhood is computed, you basically take the t neighbors that had the highest count, and here they show that taking 50 neighbors has the highest hit rate and mixed this mean reciprocal rank, where the training time was still acceptable, 78 hours compared to these. So that was pretty much it. I covered a bunch of details in this paper. I still omitted some details, but those are probably the most important details you should understand about this work. And yeah, if you found this video useful, consider subscribing and hitting that bell icon to get notified when I upload each new video. And if you have any feedback, any comment, how I can improve, or whatever you have to say, please write it down in the comment section. That will also help me boost the YouTube algorithm. So yeah, until next time, keep learning deep.